Okay, the previous video talked about the topics in the course and the definition of a rate. And in this video, we're going to talk about more sort of introductory topics, thinking about stoichiometry, reaction order, elementary reactions, and then we'll move into some tools for reducing the complexity of complex reaction networks. So this is a very typical stoichiometric equation. You see here generic compounds A, B, C, and D. And these lowercase letters here indicate their stoichiometric coefficients. These are the numbers of A molecules being consumed and the numbers of C molecules and D molecules being generated in this process. We write the rate of the reaction without specific reference to any one particular species as this symbol R, right? And this literally means the number of moles of times that this reaction occurs per volume per time, for example. Now we can relate the reaction rate to the rate of generation of any particular species involved in the reaction by using these equations, right? So the stoichiometric coefficients are what's going to allow us to turn the rate of generation of species A into this rate of reaction R. Now the reaction order is the derivative of the log of the reaction rate with respect to the concentration of the log of the concentration of a particular species. Now it's important to recognize that the reaction order does not have anything to do really with the stoichiometric coefficients, except in very special cases. So in general, we can write down the equilibrium constants in terms of these stoichiometric coefficients and concentrations of the species, but we cannot do the same kind of thing with the reaction order, which really depends on the mechanism by which this process represented by this stoichiometric equation is occurring. Now there are some special cases, we call them elementary reactions. They play a very important role in writing down mechanisms of more complex reactions. But for these special cases, the stoichiometric coefficients and the reaction orders are directly related to each other. So elementary reactions occur as written in the stoichiometric equation. They do not involve any intermediates between the reactants and the products. And the rate laws for an elementary reaction are just written down in terms of the law of mass action, right? So a couple of examples here. If you have a unimolecular reaction where species A is converting to some product, then the forward rate law for that process would be just a constant times the concentration of species A. If it's a surface reaction, you might have a surface adsorbate A that converts into some products, and that reaction would have a forward rate law that's just a constant times the coverage of species A. And sometimes you can have things that involve both. For example, you can have an Eli-Ridial step where you have a species on the surface that reacts with a species from the gas phase, and this would give you a rate law that's a constant times the coverage of species A multiplied by the concentration of the species that's coming in from the gas phase. Another case that might be kind of interesting here is the trimolecular reaction. So conventional wisdom might say that reactions that are trimolecular are rare, and when you see one, you can be almost sure that it's not actually an elementary reaction. Usually there's something happening with two of them, and then maybe the third one comes in and reacts with their product. But there are cases where trimolecular reactions can be elementary, and they are actually quite important in the theory of low-pressure gases, and we'll see that as we go on through talking about the Lindemann mechanism later in the course. There are also cases where you have trimolecular elementary steps that involve species in solution, right? So this is the methyl trioxorhenium complex that's going to react with a hydrogen peroxide. And in order to do that, it needs a water molecule to come in and serve as a proton shuttle, right? So this is pretty common that you have water molecules that are explicitly part of the reaction coordinate here. You see its bonds breaking along the reaction coordinate, so it's actually a part of the transition state complex here. And that leads to this funny situation, right, where we have water on the left and water on the right. And if we want to write this down as an elementary reaction and have the mechanism for that elementary reaction actually lead to the appropriate mass action rate law for that process, then we have to leave the water on both sides of this equation, right? So that's an important thing to keep in mind, that elementary reactions sometimes have these spectator species on both sides. So let's talk about a rate law for a process where we have a reversible dimerization, right? So two molecules of A are going to dimerize to form one molecule of B. We're going to assume that this process has a forward rate constant Kf and a backward rate constant Kb, and that this looks like an elementary reaction. Whether it is or not, we don't know. We would have to go through and do some further diagnostics to tell. But we're going to work it as though it is, and so we're going to work this in terms of an extent of reaction per volume, right? So this is a intensive version of the usual extent of reaction variable, and it allows us to write down concentrations in terms of the initial concentration minus a stoichiometric coefficient times that extent of reaction variable. And we can do the same thing for our products. Now, the rate equation is that the extent of reaction, the rate at which that changes per time, is a constant multiplied by the concentration of species A, so that's the forward mass action rate law here, minus the backward rate constant multiplied by the species of B, so that's our backwards mass action rate law. And now, you could try and go through and do some direct integration of this, but it would lead to something quite messy. And instead, what we can do is just imagine that we had an infinite amount of time passed here, and that should lead to the left-hand side being 0 when the extent of reaction variable takes on its equilibrium value. Okay, so now that gives us this equation. Without even going through and solving for the value of this xi eq variable, we can go ahead and subtract this from this, and that gives us this equation that tells us the rate at which the extent of reaction is changing can be written as a product of two terms. One that is the remaining deviation from equilibrium extent of reaction, and the other one is this more complicated term that involves a couple of constants. And we can take some of those constants and we can group them into dimensionless parameters. For example, this eta gives you this little set of constants here, and that one involves another one. This ZEQ is basically a extent of reaction multiplied by a rate constant times 4. And now what we can do is go ahead and simplify these things. When I multiply the eta by t, I find that that's actually a dimensionless time, and I can relate that to the logarithm of quantities that involve these z's and the equilibrium value of z. Now, you can go through and you can invert this equation to obtain the ratio of z with z at equilibrium, and that gives you e to the eta t minus 1 over e to the eta t minus alpha. So this is an interesting little equation because, well, first of all, note on the left-hand side we have z divided by zeq, and from our definition of z, we had that it was just a constant multiplied by the extent of reaction. So this equation basically says that the extent of reaction relative to the equilibrium extent of reaction is given by this ratio of these two exponential quantities. And now if you look into those exponential quantities, you see that at equilibrium, there should be some extent of reaction unless I happen to start at equilibrium. And at the initial time, the reaction hasn't gone anywhere yet, right? So that ratio should start out at t equals 0 being 0. And indeed, when I plug in 0 here, I get 1 minus 1 in the numerator. And as long as alpha is not equal to 1, then we have no problems here. And of course, you see conveniently that alpha can't be 1 because it's zeta over zeta plus eta. Okay, so this is showing us how we can write down this rather complicated dynamics of this dimerization process in time in a relatively simple way involving these dimensionless groups. So this is the result. This is the extent of reaction versus time, and you see here that if you moved along, if you followed the reaction in time, it would move on one of these particular curves for a given value of alpha, moving in time upward and to the right. Now, the course that it takes as a function of time depends on the value of alpha, and looking back at the equation, we can see that alpha had this definition, right? So a pretty complicated thing to unravel, but in principle, you could do some nonlinear fitting or something to actually back out these parameters and learn from them the values of the forward and backward rate constants. One last thing to say about this solution is that it's valid regardless of whether the reaction has initial conditions that make it run forward or backward, right? So this same solution works in both cases. So I think that that's where I will conclude this little section of the video. I'm going to go ahead and upload this, and we'll do the pseudo-steady state approximation, the quasi-equilibrium approximation, and the rate determining step approximation in the next video.